of determining sigma x prime and tau x prime y prime on a plane inclined using Mohr circle, and our plane this time around is going to be inclined 60 degrees clockwise. So that would be basically like if we had a situation like this and we've inclined this 60 degrees clockwise, okay? And then we're going to confirm with the plane stress equation. So we're going to get right into this. We're going to define our known values. So sigma x is a positive 150 MPa. Sigma y is a positive 100 MPa. And then tau xy is a positive 75 MPa based on our sign convention. And we're going to go ahead and calculate sigma average as sigma x plus sigma y over 2. And so when we get that, that should be 125 megapascals. Pretty clear to see that. And then we're going to define a point A. Define point A on the circle, okay? And again, point A is defined as local and global axes are corresponding with one another. So that would be if local and global axes are corresponding with one another, then the point sigma x prime and tau x prime y prime would just be equal to sigma x and tau xy. So this would be equal to 150 MPa, comma 75 MPa. So it kind of turns out, I don't know if you're noticing a pattern or not, but point A, when you define the point A as local and global axes are affiliated or corresponding with each other, then that point A is just sigma x, comma tau xy every time. Okay, so that's kind of convenient. You don't necessarily have to redraw the element a bunch of times. And then in a similar way, we're going to define point G on the circle. And with point G, that's going to be based on a 90-degree counterclockwise rotation. And so when we rotate our local axes 90 degrees counterclockwise, our sigma x prime is corresponding with sigma y, and then our tau x prime y prime would correspond with negative tau xy. So again, that would always be the case when you rotate the local axes 90 degrees counterclockwise. Draw it out to confirm, but that will always be the case. So that's why it's nice to just always use this thing called point A and point G every single time, because it's A will always be sigma x and tau xy, and G will always be sigma y and then negative tau xy. So it's kind of easy to remember. So when we punch this through, we'll have a 100 megapascals in tension, and then we got negative 75 megapascals for that shear stress, defining point G. So we're ready to draw the circle now. I'm going to scroll down to this next page just to give myself plenty of room. And here we go. And I like to put positive shear stress going up. And here is my normal stress. You need to put your units on your axes. They do carry units. So let's look at point A first. Well, here's the origin, of course, which we're not really interested in. Point A is going to be 150, 75. So here's what I do. I try to kind of scale things off so my axes are as much to scale as they possibly can be. So I'm going to go ahead and just put 150 right here along the sigma axis. And then I'm going to split this up into 50 and 100 intervals just so it's pretty evenly split. And again, you want to try to draw this as much to scale as possible. So this is about 50 and this is about 100. On your own paper, you could draw it to scale better than I can on this thing. So so that's kind of how I'm scaling off my sigma axis. My tau axis, I'm going to try to keep it with the same general scale. So that would be 50 right here. And then 75 would be probably 2.5 squares. So I'll tell you what, I'm going to move this up just a little bit. There we go. Tau megapascals. And maybe I'll just put 1, 2, 3, 4, 5. Maybe make that 100. And this will be 50. And then, so drawing this is kind of half the battle, you know, drawing it nicely to scale. So there's a negative 100, and of course that's negative 50. So let's plot these points. Point A was 150, 75. So I'd say that's like right there, point A. And then point G is 100 and negative 75. So I'd say point G is right here, point G. And remember, AG defines the diameter, okay? We've said that a couple times now. AG defines the diameter, and sure enough, there's the center at 125. Okay, now I'm going to try my best to swing a circle through this. We're going to see how good my art is on this example. Well, that is horrible, so let me try to redo that. Okay. Not that good, but I have done worse. Okay, that's probably as good as I'm going to be able to get it on this figure. Again, draw it to scale on your homework just so you're getting the right values when you're looking at this. So here we go. The next thing we're going to do, so this is the circle, right? This is the circle in general. The next thing we want to do is referencing that line AC. We're going to rotate. I'm going to make some comments up here. We're going to rotate 2 times 60 degrees, which that was our plane of interest from the problem statement, opposite of what is on the element. Okay, so earlier in the problem, I'm going to scroll up and we'll see it says 60 degrees clockwise. So I'm going to do 2 times 60 is 120, and I'm going to go counterclockwise, okay? Counterclockwise. So 120 degrees counterclockwise is going to be somewhere about right here, okay? I'm doing a little bit of eyeballing, and this is going to be it right here, 120 degrees. So this point is the sigma x prime and the tau x prime y prime point that we're interested in, okay? So then the question becomes, how do we get these values, okay? Well, at this point, we're going to do some trigonometry, okay? And there's a few ways we can kind of handle this. So here's what I'm going to do. I'm going to say, well, check out this shape right here. We have a triangle that we know some information about, okay? So first, I'm going to utilize that yellow triangle that I just drew there, okay? And I'm going to bring it out over here. And it's a bit exaggerated, all right? So what is this value right here? Well, if you look at this bottom value, that is 150 megapascals minus the center coordinate, which we got is 125. So that should be 25 megapascals. And then, of course, the height of this triangle is 75 megapascals because that triangle, again, remember, is defining point A right there, right? This is the center, and this coordinate, we know that. So can we get the radius from this? Absolutely. We get the radius of the entire circle using this one triangle, and that's just going to be the Pythagorean theorem. All right, so I'm punching the Pythagorean theorem in my calculator right now, and I get 79.06 megapascals. That radius carries units of stress, megapascals. Okay, so I got the radius now. That's great. Can I get this interior angle? Absolutely. I'm going to call it alpha, and I'm going to say alpha, a few different ways of doing this. I'm going to say it's the arctan of 75 MPa over 25 MPa. So I'm punching that in my calculator. That's just the arctangent of 3, actually. So I get 71.56 degrees. So here is that little alpha that I just calculated. Now, why did I get that? Well, we're going to find that it's going to be a bit useful to us when we're doing some manipulations later on, okay? So in particular, check this out. Look at this triangle right here, okay? What angle is this? Well, that is still alpha, okay? So we could have worked inside of the triangle that defined point G as well, okay? So I'll put a note here. Similarly, we could work with the triangle involving G, okay? And you would get the exact same numbers, okay? So there's alpha, and that will be of use to us. So what do we really need? Well, remember, we have really become interested in this point right here, okay? This point right here, which is defined by this blue right triangle, okay? And if we're interested in this triangle that I just sketched right here, this right triangle, then we need some more information about it. Well, we got the radius for sure. We know this is a radial line, no question. What we don't know is this vertical component. That is tau x prime y prime that we're looking for, and we don't know this horizontal component, which would give us information about sigma x prime. So what do we need to do? Well, we can use some angle manipulations and maybe get this interior angle right here. So the question is, how do we get that interior angle? Okay, so here's what I would do. I would say, you know that this full angle right here is 180. Okay, that's 180. And then we know that this angle going from CA to the plane we're interested in is 120, okay? So if we do 180 minus 120, so 180 minus 120, we're going to get this little piece right here, okay? So let's do that. Let's maybe, I know there's a lot going on in this figure. I'm going to change colors again. I'm going to get this angle right here. I'm going to call it beta. Okay, I'm going to put 2 tick marks there. I'm going to say beta equals 180 degrees minus 120 degrees. And that, of course, is 60 degrees. Okay, but that's not really the angle that I'm interested in. What am I really interested in? I'm interested in this angle right here. Okay, so how can I get that? Well, guess what that's going to be? How about we call that psi? Okay, I'm going to call that psi right there. I'm going to say psi is equal to alpha, little alpha, minus beta. Okay, so maybe I'll blow this up and show you what I'm looking at, okay? Here is alpha, okay? Same alpha that we calculated over here. And here's the other right triangle that we're interested in. Ooh, that looks horrible. There we go. And here's the other right triangle. Here's the point we're interested in right there. So where did we get beta? Beta was this angle right here, beta. So that psi angle is right here, okay? So we get psi equals 71.56 minus 60 degrees is 11.57 degrees. Now, you got to be very careful when you're visualizing this. Draw out as many of these right triangles to help you as you need, okay? Don't try to be a hero and just say, oh, I can see it clearly, because even I can't see it that clearly. I had to draw these triangles out myself, all right? So now we're going to operate in this blue triangle. All right, here is the psi value, that psi equals 11.57 degrees. This vertical component, guess what? That's the tau x prime y prime component we're interested in. And we know the radius already. The radius was calculated as 79.06 megapascals. And then this horizontal component, I'm just going to call it, how about I just call it x? That's going to help us get our normal stress value, okay? That is not the x, the thing that I just drew as x, that is not actually sigma prime x, but it helps us get sigma prime x. All right, so here we go. We can just go ahead and get tau x prime y prime as the radius times the sine of that psi value, okay? And we can put a negative out in front of it because it's going into quadrant 4 where tau is negative, okay? So tau x prime y prime ends up being, let's see, negative 79.06 times the sine of 11.57. So I get a negative 15 point, oh, I didn't mean to scroll. Negative 15.87 MPa. Guess what? That's one of my answers, okay? Now I need this x value. I'm going to say x equals radius times the cosine of psi, okay? And so x equals 79.06 times the cosine of 11.57. So that's 77.45 megapascals. But is that sigma prime x? Not really. Here's how you get sigma prime x. Sigma prime x is the value from the origin to this point right here, okay? So it's the origin to here, okay? That's sigma prime x. What we just got, which we called x, was this value right here. So how do I get sigma prime x? Well, it's going to be the center coordinate minus that x value, okay? So if you look back at your figure, sigma prime x is the center coordinate, which is really sigma average minus x, okay? So sigma average, what was that? I believe that was 125 megapascals. Yes, I had to scroll up and check it. So 125 minus the 77.45. So I get 47.55 megapascals. So again, sigma x prime, 47.55 megapascals. And then tau x prime y prime is negative 15.87 megapascals. And again, that negative associated with tau xy is indicating that we're in quadrant 4, okay? Now we need to check with plane stress equations. I just like to do this to make sure I did things right, because I make mistakes occasionally. So sigma x prime is sigma x plus sigma y over 2 plus sigma x minus sigma y over 2 times the cosine of 2 theta plus tau xy sine of 2 theta. Okay, and so when I start plugging in values, my sigma x was, let's see, 150 MPa plus 100 MPa over 2 plus the quantity 150 MPa minus 100 MPa over 2 times cosine of 2 times theta. Now, remember, at this point, we're just checking as if this was a regular old plane stress problem. So theta is, remember, theta was 60 degrees in the element going clockwise. So that should go in as a negative. So I'm going to have 2 times negative 60 degrees there. And then, of course, we have plus 75 megapascals times sine of 2 times negative 60 degrees. So a lot of room for calculation error. So let's just be careful here. Make sure those negatives get input in properly. And let's see, 150 minus 100 is 50 divided by 2 is 25. And then I'm doing my calculations a little out of order from how I wrote them. Okay. And then plus 150 plus 100 divided by 2. So sure enough, I get sigma x prime as the same thing. I get 47.55 megapascals. That checks out. And then I'm going to check on my tau x prime, y prime. That's negative the quantity sigma x minus sigma y over 2 times sine of 2 theta plus tau xy cosine of 2 theta. And let's check this out. Negative the quantity 150, and put your units in everywhere, please. 150 minus 100 divided by 2 sine of 2 times negative 60 degrees plus 70 megapascals cosine of 2 times negative 60. Again, that negative 60 indicates a clockwise rotation as was specified in the problem. So let's see, we put in those negatives for the angles. And I'm just punching things through carefully right now. Okay, times 150 minus 100, so that's 25 times negative 1.0. And then I'm going to add that to this. So I get, sure enough, I get negative 15.85 megapascals, and I got the same thing, a little round off error there. So, you know, on a test problem, or when we move into later courses, you don't have to do all this with Mohr circle and then check with the equations. In fact, the point of Mohr circle is so you don't have to do all of these equation number crunching, okay? So that's the whole point of the circle, but since we're just kind of getting stabilized with this process, I like us to check our answers with the equations and make sure we get the same thing. But as we move forward, we don't necessarily have to check always with our answers. I just like to check every now and then to make sure I haven't, lost my mind or doing anything completely wrong.